Imagine somebody on Earth tells you that, you are not alone in the universe. A team of astronomers from Cambridge have detected the most promising signs of a possible biosignature outside the solar system. Joining us is Dr. Nikku Madhusudhan, an Indian origin astrophysicist at the University of Cambridge, who has made headlines with a potential discovery of alien life on a distant planet called K2-18b. Thank you for joining us, Dr. Madhusudhan.
Thank you for having me here.
So to begin with, we would ask you to describe your journey from IIT to Cambridge. What inspired you to delve into the world of astrophysics?
Yeah, so I've always been fascinated by basic sciences, math, physics, chemistry, growing up. And in my undergraduate, like most Indian youngsters, I pursued engineering, even though I had the opportunity to explore a lot of basic science subjects and projects. But when I went to graduate school to the US, this astrophysics I got introduced to more basic physics. And astrophysics was something that I felt I was suddenly passionate about. So I was pursuing that. And that was also the time when exoplanets were just being discovered and their atmospheres were just being observed. So I felt that was a very promising area to pursue graduate studies in. So I entered to do that. So my PhD involved developing the first atmospheric retrieval techniques for exoplanets. So we invented how, if you observe a spectrum of a planet, how you extract the chemical information of the planet's atmosphere. So that was my PhD thesis. And thereon, one thing led to another. So lots of data started coming over the last close to 2 decades now. And we have been working on pretty much every instrument that is capable of observing exoplanet atmospheres. I have been fortunate to be involved. And just in the last 5 years, there is this new domain that is opening up the ability to study atmospheres of small planets. And this is a rich new territory. So this is where our focus is right now. But the passion for astrophysics started like through my graduate studies, even though I was interested in basic sciences from the very beginning.
Right. So, as we already know that ancient Indian astrophysics is rich and diverse, be it with respect to the development of sophisticated astronomical theories or instruments. Have you ever based your understanding on Aryabhatta, Brahmagupta or Varaha Mihira?
So not directly. So I've heard of them, and obviously growing up in India, you hear about all the greatness of Indian science from ancient times. But we have never actually, like at least in my journey, never actually practically used any of those principles in our own research in modern science. But I think just as part of growing up in the Indian environment, you imbibe some of the philosophy behind the pursuit of knowledge in principle, and I think that has shaped many of my choices of how I pursue science and life in general.
So if you could tell us one philosophy from the Indian arena which has really helped you?
Oh, I mean, the very basic one is the idea of a global humanity, that we are not confined to national or geographical boundaries, and that we have always been thinking of the world, at least the earth, as one place and just one people. I think that strikes very well to the very core of what we are pursuing right now, is when we are trying to look for life elsewhere, you suddenly realize that looking from the earthly perspective, we are all inhabitants of the same cosmic entity, that's the earth. So that sort of is very much in line with what we are already used to thinking growing up, if you're in tune with the core Indian philosophy. So I'm very comfortable with that narrative. So this doesn't come to me as a surprise, what I'm going through now.
Right. So now shifting our focus on your recent discovery, walk us through the major findings on a possible extraterrestrial life on K2-18b.
Yeah. So upfront, as you may have seen from various sources, we are extremely careful in saying that we have not actually detected life. We are not claiming that we have detected life. What we have detected are initial signs, tentative signs of 1 or 2 molecules that we know on Earth are uniquely produced by life. and have been predicted to be good biosignatures elsewhere as well, like on other planets as well. These are theoretical predictions, but this is the first time those theoretical predictions have actually been observed. So that is the major breakthrough, is that for the first time in the history of our species, so far astrobiology has been a theoretical subject. So for decades, people have been studying what kind of life would be elsewhere, what could their signatures be, but it has always been theoretical. And the paradigm shift that's happening right now is that for the first time, we are seeing some signals on a planet that we think is habitable theoretically, but we can actually observe them. So that the very fact that we're able to observe anything about the atmospheres is the paradigm shift. Now, the icing on the cake is that what we are observing, the signals that we are seeing, the molecules that we are seeing potentially, have also been predicted to be possible biomarkers, and that's a big deal. Now, it could be that we'll get more observations and they may turn out to be different from what we are seeing right now. So this signal may be false. It is at a good level. It's at a good level of confidence, but we still want to be extremely robust. So when we obtain more observations, the signal may go away. It could also be that we may detect the signal very strongly, but then some theoretical study may come up in the future and say, actually, we can make these molecules from some other means that is not biological. That's also fine. We want to remain open to all those possibilities. But the principle stays the same, which is that this is the first time we are even able to have that debate based on actual observational data. And that brings us into this whole new era of observational astrobiology. And that's the paradigm shift we are talking about.
Well, indeed, it is for the first time, as you've correctly mentioned. But how did NASA's James Webb Space Telescope really help you to spot gases which are possibly linked to life?
Yeah, so the James Webb Space Telescope, JWST, is the centerpiece of this finding. That is what allowed us to make this finding. Until 2 years ago, we didn't even have this capability ever. So this is the largest space telescope ever in the infrared. So the method is called transit spectroscopy. You're looking at the star as the planet goes in front of it. So some of that starlight passes through the atmosphere of the planet before reaching the telescope. Now, the molecules in that atmosphere absorb some of that starlight that is passing through. So by measuring how much absorption is happening of the starlight, we can invert that and say what is the composition of the planet's atmosphere that is causing that absorption. Now, this technique, we had known it for 2 decades now, and we have used it with other facilities. But the importance of JWST is the sensitivity. Because this is the largest mirror ever in space, in the infrared at least, sensitive in the telescope sensitive in the infrared, this can pick up very, very small signals. We are talking about tens of parts per million, hundreds of parts per million signals. We can still pick them up with this telescope, and that's what made a huge difference in this finding.
Well, Dr. Madhusudhan, you and your team have literally witnessed this firsthand. The planet K2-18b covered with a warm ocean brimming with life. Could you take our viewers through your telescopic lens? What did you witness in the first place?
So the inference that you just mentioned, the picture that you just mentioned, is an inference from the spectroscopic observations that we are getting. So for example, 2 years ago in 2023, we reported the first detections of carbon-bearing molecules, methane and carbon dioxide, and we did not detect some other molecules like ammonia or carbon monoxide. Now that combination of species, and given where the planet is located, it's located in the habitable zone of its host star. So all those factors together means that the best way we're able to explain those chemical observations if there is an ocean under a thin hydrogen-rich atmosphere. Because any other combination of internal structures and atmospheric extent doesn't explain all these observations that we are seeing. So you get the chemical information of the atmosphere, then you use theoretical models to see which model will explain the data best. And the only model currently that explains all the observations that we know of is one where there is an ocean. And especially if this DMS or DMDS detection is real, then the only way based on current knowledge to explain that is an ocean world with life on it. Of course, as I already mentioned, we still want to be careful. We want to remain open to other possibilities that may come up. These are called unknown unknowns in science. We don't know. There may be other processes. So we want to remain open. But based on current information that we have, that is our best explanation.
But if you could have to explain it more in visual terms, what did you see? in the first place? What were the kind of visuals that you came across?
So the visuals, actually, when you look at a planet, you are actually not seeing a planet. It's always indirect inference. You're seeing the spectrum of the planet's atmosphere. And from that spectrum, which is light as a function of wavelength, you see several peaks in that spectrum. And based on those peaks, you're able to identify whether this is, let's say, due to methane or carbon dioxide, or due to DMS or DMDS. And that is what we are seeing. We're not actually seeing the surface of the planet. We can't actually resolve the planet itself. We only can infer it indirectly from the spectroscopic observations, like most of astronomy. Like this happens for a lot of astronomical objects. Now, what is important to mention here, that even 2 years ago, when we looked at carbon-bearing molecules for the first time, that was the first time in history that carbon-bearing molecules have been detected on a habitable zone exoplanet. So even the very act of detecting as basic a molecule as methane or carbon dioxide is a big deal, because even that had never been seen. But
Right.
now if we are going one step beyond that and measuring molecules like DMS and DMDS, that is a big deal, because those molecules here on Earth are uniquely known to be produced by life, and they're produced in very small quantities. On Earth, they're produced at a level of 1 part per billion, for example. On this planet, we think it's thousands of times higher, if over a few parts per million at least. And that is the major breakthrough, that we are even able to even detect such molecules in the atmosphere of a planet 124 light years away, and we are not even seeing the planet, we're just seeing the spectrum of its atmosphere, and that is a paradigm shift.
Well, that indeed is a major breakthrough, as you have correctly mentioned. But having introduced the concept of Hycean planets, could you break the etymology of this word coined by you? Like, how unique is this planet?
Yeah, so this concept of a planet called Hycean worlds, the word Hycean stands for, it's a portmanteau, a combination of hydrogen and ocean, basically. So 5 years ago, we came up with this concept even before the JWST observations were made, because we were already at that point studying K2-18b theoretically. So we knew the mass of the planet, we knew the radius of the planet. There were very early indications that it could have a hydrogen-rich atmosphere. So we asked ourselves the question, well, is there any way this planet could be habitable? And the way to establish that is by running a lot of theoretical models of the planet's interior and atmosphere together, and see what are all the possible conditions that could explain the bulk properties, the mass, radius, equilibrium, temperature, and so on. And we found that there was a small range of solutions that did allow for liquid water. And then we took it further and said, well, if there is a small number of solutions that are possible on K2-18b, how many other planets are out there which could also fit that description? So we introduced this new class of planets called Hycean worlds and explored that space, and we found that there could be up to about a dozen planets that can also fit that category. And then we proposed for these James Webb Space Telescope observations, and we got the first observations 2 years ago, and that fit the description of what we were expecting and what other people have also been expecting in terms of their chemical composition. And then now the evidence of these molecules, if this turns out to be true, only adds to that narrative that it could be an ocean world. The Hycean world is basically an ocean-covered surface with a hydrogen-rich atmosphere. All of this together adds to that narrative that could be a potentially inhabited Hycean world, and that's very promising, but we want to remain open.
Well, so how long will it take to confirm realistically that life exists beyond Earth? Will this discovery also confirm that life is very common in the galaxy?
In terms of practicalities, there are two aspects here. One is making sure the signal we are seeing is real, that it is indeed due to DMS or DMDS or both. And that can be done on the order of 1 or 2 years with James Webb Space Telescope, with a small amount of time. We are only talking about 16 to 24 hours time. JWST observes for thousands of hours every year. So that's a small amount of time, but it can be done on the order of 1 to 2 years. So once we establish that these molecules are real in the atmosphere, then there is also the parallel effort that is needed to establish that these molecules can only be produced by life on this planet. It has been predicted to be the case, but we want to remain open and do many more tests to make sure that that is the case. So that could take us a couple of years, several more years, but that is a bit open-ended when we would conclude that. But I can imagine in the near future that we should be able to establish it, but the theoretical aspects, we just have to remain open-ended and not put a date on it.
Well, let's hope for the best. And how has your research actually opened a new window into life beyond Earth? Like in general, what is the scope of this discovery?
Yeah, so until 5 years ago, if you ask someone how long would it take to detect biosignature in an exoplanet, the answer would have been 15 to 20 years. We needed the next generation of facilities. With this research, that frontier has come to now, basically. So we are saying we have the facility right now to detect these molecules right now. Whether they're actually due to life or not, we can argue, we can debate on it, but the observational capability we have right now, that's what this study has demonstrated, the observational capability. So, and that is opening a whole new area. It basically is the beginning of observational astrobiology. So in the search for life that we have been as a species thinking about for thousands of years, I think going forward, we would look back upon this time and think of it as when the paradigm shift happened, is when like we as a species have demonstrated for the first time that if there is life out there of this kind, then it is actually observable. So that is the paradigm shift we are talking about. And going back to your previous question on what does this imply for life out there, the principle here is that if you can establish life exists on one planet out there, then just by extrapolation, it is very easy to imagine that life should be common out there because there are so many planets out there. There are billions and billions of planets out there. So that is the major transformational moment we are talking about. And we hope these signals stay and that we are able to confirm. But the important thing also is that there can be only one of two ways, right? If the signal is real, we are either detecting a sign of life or we are detecting an entirely new chemical process that we have never seen
Right.
on Earth. Either of those ways is a major breakthrough for science. And especially in habitable environments, this planet is in the habitable zone of its host star. It's slightly bigger, so it's not like Earth. And previously we had been focusing on Earth-like planets, but now we are saying that there could be other kinds of environments that could also be habitable. And these are all the things that are creating like a whole new paradigm in our search for life elsewhere.
Oh, well, in fact, before I let you go, Dr. Madhusudhan, I want to ask you one last question. On the same lines, as S. Somnath, former ISRO chief, had also reiterated on this fact that there does extraterrestrial life exists somewhere in the universe. On those lines, how does the future look like?
So I think most people would agree that just by the sheer scale of the universe and the sheer number of planets out there, it's very easy to make the argument that there's got to be life elsewhere. The question is what kind of life? So in my mind, simple microbial life, I don't think most people would argue that that is even a question. I think like simple microbial life, like when the Earth started many like billions of years ago, when life started on Earth, it started as like very simple single cellular microorganisms, right? So that kind of life, I think, should be common and should be like right now with these kinds of planets, the Hycean worlds should be detectable. But then if you're talking about multicellular life, complex life, and especially intelligent life, that is the gray area. We have no constraints, no idea on how common that would be. So we can't comment, especially I can't comment on that. But for simple microbial life, it's got to be out there. And even if we detect that, it will be one of the biggest discoveries in our history, because on Earth, one of the biggest questions is that how we don't even know how life originated here on Earth, right? So even the
Right.
formation of the simple life forms is a big open question here. So if we detect that elsewhere, it might give us constraints, some information on how life originated right here and how common or rare that process is. And that once you fix that initial condition or understand that initial condition, a lot more other avenues could open up in the search for life and understanding life elsewhere. So that is the big breakthrough that
Well, all
we
the
would be looking
best to
forward
your
to.
future endeavors as well. Well, it was our pleasure to host you, Dr. Madhusudhan, and also to celebrate this transformational moment of yours and your team, which is searching for life beyond the solar system. Thank you once again for speaking to Republic TV.
Yeah, thank you very much.